everyone, I'm Chris Mori, and I'll be presenting a joint work with Pranjal Awasthi and Karina Cortes of Google Research. Our paper is called Theory and Algorithm for Batch Distribution Drift Problems, and in it we study concept drift, a field in machine learning where distributions are allowed to drift over time. This is particularly important in real-world applications because our target concept is often changing and the learning environment is not stationary. One example of this is sales predictions, which can vary significantly from season to season, where a product may be more or less in demand. Others are financial market prediction and political sentiment analysis, which can also naturally vary with changing markets and changing political environments. In these applications, the standard assumption that train and test distributions coincide does not hold. We have a more challenging learning problem because if we were to train on all past data belonging to potentially different distributions, we might have poor performance. But instead of simply discarding all old data, we ask the question of how we can use it to improve our predictions. In our learning scenario, we have t source distributions occurring in this sequential way, and the t+1th being the target distribution. The learner receives samples S1 to ST+1 from each of these distributions, and we make the assumption that the data is IID within each sample, which makes it slightly more favorable than time series prediction. ST+1 is typically only of moderate size compared to the other samples. Our goal is then to achieve small expected loss on the target distribution dt+1. One of the key ingredients in our work is the use of discrepancy to measure distance between distributions. This is the first equation on the slide, and to measure the distance between distributions di and dj, we measure the supremum over hypotheses of the difference in expected loss. As opposed to other distances, like the L1 distance, this takes into account the hypothesis set and loss function, making it more suitable for our learning problem. One of our main results is then a generalization bound for dt+1 in theorem 1, which we have included at the bottom. We have a weight vector q over our sample, and our bound is in terms of a q-weighted empirical loss, a discrepancy term which recommends less weight of q to samples with high discrepancy, a q-weighted Rademacher complexity term, and a term with the L2 norm of q. This then motivates our S-drift algorithm, which minimizes the right-hand side of this inequality through an alternate minimization of both Q and our hypothesis H. We compare our S-drift algorithm to many baselines in our experiments. The first is naturally training on the target only. Beating this baseline would mean we make effective use of past samples. Other baselines are kernel mean matching, MM and DM, which are two-stage optimization algorithms, and EXP, which exponentially downweights past samples. We also have BSTS, a time series algorithm. Our work can also be used for multiple source adaptation, where one would not assume any sequential nature of our samples. We therefore compare with two state-of-the-art MSA algorithms, MDAN and DARN. We compare on both classification and regression tasks. The results here are for real data. Classification is measured with accuracy relative to training on the target. Therefore, we're looking for a score greater than 1. Our standard deviations are obtained through cross-validation, and the best results are in bold. Regression is measured with mean squared error relative to training on the target. So in that case, we're looking for a score less than 1. Most of our datasets are from the UCI repository, and we break them up into t+1 samples, most often using the time component to do so. For example, in electricity, we have data from 1996 to 1998, and the goal is to predict when the price of electricity in an Australian market is moving up or down based on a 24-hour moving average. Each source segment is 2 months long, and the target is slightly shorter. We observe that our algorithm generally outperforms our baselines. Taking a closer look at how exactly S-drift achieves this performance, we analyze the average probability mass assigned to each sample from Q, our weight vector, versus the normalized discrepancy of the sample. We expect to see higher mass allocated to lower discrepancy samples, as these more closely match the target distribution. The last pair of bars in each graph corresponds to the target, which naturally has higher mass and no discrepancy. And the others are the source samples. As we want to see, when the blue bar is high, the green is low, and vice versa. So, our algorithm effectively gave higher weight to useful samples and lower weight to ones that were far from the target distribution. We recommend use of our algorithm in appropriate settings, and thank you for your time.